Okay, so let's go back to the nonlinear Schroedinger equation. The first time we express it the following way. Um, I dt u minus Laplacian u lambda u alpha minus 1 u, okay, ux0 u0x t in r, x in rn, lambda and alpha are real, but at first we established that alpha greater than 1, okay? And we had the integral expression it Laplacian u naught plus I lambda t ei t minus t prime Laplacian u alpha minus 1 u t prime dt prime. This was the integral expression. So the first theorem, the local theory in L2, established first as a condition that alpha should be between 1 and 1 plus 4 over n. This was, let's say, the critical case. Okay, so for example, if we have one dimension, we will have that alpha is between 1 and 5. Okay, so for example, let's choose alpha equal to 4. In this case, here we will have u, absolute value of u to 3. We will have the same here in the integral. Okay, so in this case we have one dimension. Let's say that the exponent is equal to 3 because alpha is 4. Okay, then so alpha is equal to 4, then we will have a unique solution u of the integral equation in the time interval, say minus dt. Okay, and where is u going to live? U will be in c of minus dt L2 Rn. Okay, intersection Lr minus dt L alpha plus 1 Rn. So we know who is alpha, 4, so this is going to be a 5. What about this R? R is 4 alpha plus 1 and over n alpha minus 1. So what is going to be R in this case? Well, this is 4, 5, 5, 20, 1, and 3. This is our R. We can say that in this case R is going to be 20/3. So R is between 6 and 7. Okay, so the solution is going to be in this space, but intersection L, let's say R, this is between 6 and 7, and in the space L is going to be 5. Okay, but if we take in consideration the corollary, then we have that the solution U will belong to LQ and LP for LPQ defined by all these conditions. So now we can see that what happens if we have one dimension? So then the u is going to be, the solution u is going to be, well, we are in this case. So the corollary tells us that it's going to be in L2 of minus tt L3 Rn and this for all pq satisfies this, and 2 over q equals n2 minus np. So for n equal to 1, we have that p is between 2 and infinity. Okay, so this p is going to be between 2 and infinity. What about q? Well, in this case we know that n is equal to 1, then we will have that 2 over q is equal to 1 over 2 minus 1 over p. Okay, so if p is equal to 2, then we will have that 2 over q is equal to 1 to 0, okay, and if p is equal to infinity, this says that q can be infinity, and if p is equal to infinity, then 2 over q is equal to 1 half, okay, so we will have the 4 is equal to q, okay, so u can be in, well, L infinity of minus t L 2 of Rn, and u can also be always in one dimension in L well, L2 is 4 minus tt L infinity Rn. Okay, so what about the critical case? This will be alpha equals to 1 plus 4 over n. So now we can take, if we want, alpha equal to 5 for n equals 1. Okay, and then for these conditions, we'll have that u is going to be in c minus t L2 Rn intersection L sigma minus tt L sigma Rn, and sigma is going to be 2 plus 4 over n. So in our case, sigma is equal to 2 plus 4 6. This will tell us that in the case where we have one dimension, the solution is going to be in, well, c minus dt L2 Rn intersection L sigma L6 minus dt L6 Rn. Okay, this is in the case where our equation is the following, but with the exponent of absolute value of u alpha minus 1 for t prime dt. So we have also always have to have u not L2. This will give us a u in this space. Okay, this space in this case, where we're considering n equals to 1.